Imagine teaching a class where each student learns from the previous student's notes. At first it works fine, but over time the notes get sloppier, details get lost, and soon everyone's learning nonsense. In essence, this is model collapse. The idea that when AI learns from other AI-generated data, its performance gradually degrades. We wanted to answer a few questions, namely, what really happens when newer AI generations train on the previous generation's data?
As AI-generated content floods the internet, future models will inevitably train on an increasing data that isn't purely human-created. Our question was, how does this affect the rate at which quality of AI output changes over time? If every new generation of AI learns from slightly degraded data, will the whole system collapse or stabilize? Based on the findings of Shumailov and other authors, we make the following assumptions. Synthetic data degrades the quality of AI output over generations, and human-produced data increases that quality. We further add to these assumptions using the findings from Rutko and other authors, where the best possible quality for AI-generated output is equivalent to the quality of human-produced data. We reason that quality in this sense is intrinsically dependent on the training pool.
Before we explain our model, let's define some terms. Let's call the amount of human-generated content on the internet to be some function of time, h of t, and similarly, the quantity of synthetic AI-generated content is s of t. We describe the abstract quality of a model's output to be some function of time, q of t, where a q of t value of 1 is equivalent to human writing, and a value of 0 being completely random outputs. We wanted to find a way of describing how the quality changes between each generation, represented by the time derivative of q. Firstly, we have the proportion of the total content in the dataset produced by humans. Then, because as the quality of the outputs approaches that of human writing, there is less for the AI to learn from, we add a factor of 1 minus q. Next, we add a term representing the quality-adjusted proportion of AI-generated content in the dataset. And finally, we add some scaling constants, lambda and gamma, representing how effectively the model is capable of learning from human-generated information, and how strongly performance is degraded by the presence of AI content, completing the model.
Next, we had to find functions for h of t and s of t. For h of t, we believe that a simple linear model is appropriate. This model takes the form h of t is equal to at plus b, where b represents the pre-existing body of work produced by humans before AI was invented, and the a term represents the production of new human content per unit time. S of t is more complicated, and we found two plausible models. First is a simple exponential model. As large language models grow faster and GPUs more powerful, the production of AI-generated content has grown exponentially with no sign of slowing down. If this trend holds, the production of AI-generated content could be modeled as a function of the form s of t is equal to c times e to the power of kt. Alternatively, rather than AI content being strictly guided by human prompts, we can model it as human content scaled by a logistic curve, showing how AI spreads as more people start to use it, where s of t is equal to h of t times c divided by 1 plus e to the power of negative k times t.
This differential equation was difficult to solve analytically, so we elected to use a numerical approach. We tested two different scenarios while simulating this model. We found that in our exponential scenario, model collapse will always occur, even in the best case where the model experiences weak degradation from AI content and is able to learn from human content efficiently. This quality always trends towards 0. To simulate this best case scenario, we set b to 400 to account for the large quantity of pre-existing training data, and c and k are kept low to simulate the slow takeoff of the quantity of AI-generated data. A is then set to 10 so that it is high in comparison. Lambda and gamma are set accordingly to the learning efficiencies of the AI model and the tendency of synthetic data to degrade performance. In contrast, our logistic scenario avoids model collapse, with the quality stabilizing at some non-zero value. Of the 6 parameters in this model, we found that the only 2 that had any impact on the behavior of the model were lambda and gamma. In the exponential growth scenario, we found these parameters influence how quickly model collapse occurred, and in the logistic growth scenario, gamma in particular seemed to affect the eventual quality the model stabilized at.
We began by highlighting that the quality of AI outputs depends heavily on the data it is trained on. When that training pool becomes dominated by synthetic content, the overall quality tends to degrade. This happens because AI models learn by approximating patterns. They become very good at producing what's common, but often overlooking the rare, diverse, and marginalized information that gives data its richness. Now, when these systems start learning recursively from other AI-generated outputs, in other words, when they begin feeding on their own data, the problem compounds. Over time, the model starts producing results that are overly simplified, repetitive, and even irrelevant. It's these layers of approximations building on top of one another that eventually lead to what we call model collapse. Our simulations show that this collapse occurs when human-generated data grows only linearly, while AI-generated data grows exponentially. We also examined a second scenario where human adoption of AI tools follows a logistic curve. In this case, quality initially declines slowly and then stabilizes because a portion of the human-created data continues to exist within that training pool across generations. In contrast, under the full model collapse condition, AI-generated data eventually overwhelms the human input. As a result, output quality drops dramatically and trends to zero. This directly aligns to the findings of Shumailov and other authors. To counter this, our findings suggest that human data must be continuously reintroduced into the system. This diversity helps preserve the richness of the training pool and maintains the quality of AI outputs across multiple generations. Finally, it's important to acknowledge the limitations of our model. We simplified multiple AI systems into a single representative model, which means we didn't account for the possibility that different AIs, each trained on their distinct datasets, could collectively provide a more detailed and balanced training base. And secondly, we assumed that output quality depends solely on human-generated data, implying that human content is inherently superior. This overlooks the potential for AI to improve existing content.
In future work, we could take this further by modeling it as a system of differential equations, where in that setup, each model could have its own values for parameters like lambda, gamma, c, and k.